Good afternoon. All right, so we are talking about some radicals today. We're going to talk through the reactions that we did in class today, especially going through the MBS ones, trying to really make sure we understand that concept and get that honed down. So let's do a little bit of radical stability and then talk a little bit about just our normal brominations. So radical stability is the same thing as carbocation stability. Think of like primary is less stable than secondary, then tertiary, then primary with resonance, then primary with more resonance. Same concept follows for radicals. We're just not charged anymore. So for forming radicals, typically speaking, for these bromination reactions, they heavily favor forming tertiary over something like a primary position here. So when we take a bromine, excuse me, a halo, no, just an alkane here. Something like this, throw in Br2. It's going to dramatically favor. We've got a bunch of primary positions. A secondary, a quaternary over here, and a tertiary. It's going to dramatically favor that tertiary position. Chlorinations are where things get a little bit trickier. So if we think about our mechanism, we make a Br radical. Bromine's pretty big. It has 35 electrons in it, so gaining an extra one isn't that big of a deal for it. It can hold on to it. It can be kind of picky, is usually what I say. It's not reactive enough that it'll just want to react with anything. It's going to really be selective for trying to pull off this tertiary hydrogen. It's not going to go for a secondary or a primary one. With a chlorination, because it's smaller, it's got less electrons on it, it's going to be a lot less picky. It really just wants to get rid of this radical as quick as it can, and it's going to reduce its selectivity by a good amount. So our normal selectivity for a chlorination is going to be, so our chlorination selectivity factor, I'm abbreviated as SF. Is going to be 1 to 4 to 5 here. And that's going to be per hydrogen. So per number of hydrogens. When we look at these, we need to kind of correlate different groups together. So these three CH3s are all symmetrical. We can say that these ones are going to be the same. If we were to chlorinate in one of those positions, it would give us the same product as chlorinating on another one. Same thing over here. These are going to be a different group. If you were to chlorinate in one of these two, I kind of got the tertiary center there. They're also going to give you the same product, but it'll be a different product as the ones that are in red here. So when we're doing our statistics for our chlorinations, let me blow my nose real quick. we're going to be looking at this as two different groups here. So, whoops, that's the erase. We'll have 9 hydrogens on this center. And then 6 hydrogens on these two centers combined. So if we do the math for this red, it would be 9 times its selectivity factor. These are all primary centers, so it has a selectivity factor of 1 over here. Versus in blue, this is a selectivity factor, or sorry, still there's 6 hydrogens. So number of hydrogens times the selectivity factor, which is again is 1. As we look at the secondary center, I'll run out of colors at some point. I've got 2 hydrogens on this secondary center. Its selectivity factor is 4, so it could be 2 times 4, which is equal to 8. And then our last center here, just gonna draw black, is tertiary. There's only one of it, so 1 times our tertiary over here has a selectivity factor of 5. So from this, we can determine that chlorinating is most likely to happen on one of these primary positions because it gives us the highest likelihood of that based on our math. So then our major product would be putting a Cl over here. Are there any questions about this?
Yes, on the primary position. Why can't we just add like the 9 and 6 together since all of them instead of making them separate?
So it's because when you make the product, like for instance, if we chlorinate here, these are the same products. They're just rotational isomers. Same thing if we had it here. All 3 of these centers are essentially the same. These are all the same molecule. So we're going to add it together because of that. Same thing with over on the other side. I put a chlorine here versus putting a chlorine here. Those are the same molecules. Now these are not the same as each other. So like this and this are not the same. So we have to separate them into 2 different groups. But because the red and the blue were making the same product, we grouped them all together. Does that make sense?
Yeah, it makes sense. So if I had put the chlorine on the right side, that would be wrong.
Correct.
Okay, thank you.
You're welcome. All right, I'm going to give you guys 3 of these, give you some time to work through them, and then we'll do some NBS reactions. Did we do this one? I don't think so. I'm going to give you guys about 8 minutes to try to do this one, these two. Actually, let's take 5 minutes to do the first one, and then we'll go through that one. I'll give you another 5 minutes to work on the second one. So we'll meet back here at 12:35, 31. we'll talk through that one and then we'll break down and do the other one again. All right, so let's break down this one. I'm gonna give you a little time to do the other one. So we've got a whole lot of different positions here. Let's start with the primary ones. It's gonna be a lot of symmetry. So there's gonna be a big amount of symmetry here, as well as here later on. Start with all these. Primary H's. These are all the same. There is a total of 12 of them. So we're going to put these 12 together. There's also going to be another set. So I'm going to call these 1. Another primary one over here. These would not give the same product because they're in a very different spot. We're going to call this 2. Well, this 1, 2. So 2 has 3 hydrogens. Most likely not going to be your major product. Let's look at some secondary positions. We've got 1 here, and then 2 symmetrical ones here, as well as another one here. So I'm going to call this one 3. These 2 I'm going to call 4, and then 5 in this bottom one. So just to kind of give us an easier way to read this, 3 has 2 hydrogens on it. 4 is symmetrical, so we're going to use both of them. It's got 4 total hydrogens. And then 5 just has 2 again. We got 1 tertiary, we'll label it 6. So 1 hydrogen, selectivity factor of 5, total of 5 here. So our major product is going to be chlorinating at position 4 here. Redrawing our molecule. And then either these are both symmetrical, so it doesn't matter which one I'm going to put on the top here. You could also have drawn this, and that would be the same product. Any questions on this one? Okay, I'm going to give you guys till 12:37 to go through the other one. I'm going to redraw it back up. I'm going to leave this up for a minute. So I'll draw it over here, and then I'll redraw it in a minute back in the full spot. In case anyone's still writing. So we'll be back at 12:37 to talk about this problem. In about a minute or two, I'll erase the rest of it and then move that into the main spot. Okay, so let's start with our primary positions. We've got a bunch of them. We're going to have a lot of symmetry in this molecule, so pretty much everything here is going to be the same. These two are going to be the same. And then these two here are also going to be the same. So let's start with these terminal H's. There's a ton of them. Got 9 on each side. Your major. So that is a total of 18 hydrogens. I'll label these 1. All right, 3, 6, 9, yep, 18 times 1. We've got another set. Symmetrical ones over here. I'm going to label these guys 2. So there's a total of 6 hydrogens. Got a last one over here. There's just 3 on that one. Doesn't have symmetry to it. We've got a couple of tertiary centers. So these 2 are going to be symmetrical. I'm going to call them 4. There's 2 of them. They are tertiary, so their selectivity factor is 5, giving us a total of 10 here. And then this last one in the middle, we'll call it 5, is just 1 by itself. So it'll also have a selectivity factor of 5. So based on these numbers, clear winner is going to be one of these terminal ones. There are 18 versus 10, 6, 5, and 3 here. So our major product should be chlorinating one of these positions. I'm going to put a star next to the other ones you could also have chlorinated at, and it would have been the same. So any of these 6 positions would give you the correct product for this reaction. Any questions on these? Okay, let's talk through some NBS reactions. So I didn't really talk about what NBS is in class. It's like a very large molecule. It looks something like it looks like this. It has a really hard time getting and actually attacking at these alkene centers. It's much more likely to pull off hydrogens that are away from them, which are more acidic. It acts a little bit more like a base than it would a nucleophile, although we're dealing with radicals, so it's all kind of different. But essentially what this does is it always extracts what's called an allylic hydrogen. So allylic is just one position away from your double bond. You can have multiple sometimes. For instance, let's take this double bond here. We're going to have an allylic position here, here, and here. You can draw on one hydrogen on each of them. And anytime you have an allylic position, NBS is going to make a radical there. So let's take a look at our possibilities for, let's do this one here. It's a little bit more interesting. So I'm going to erase this NBS. You guys don't really need to know the structure of it. we had an NBS and light. We are going to make a bunch of radicals. So we can make a radical at any one of these positions. There are 3 of them. So I'm just going to kind of go through them systematically. We can make one here. We can make one here. And we can make one here. And pretty much anywhere we make a radical is where we're going to get a product. So if there was a radical there, there can be a bromine there in the future. So we can go ahead and just start drawing in products at these positions. And then from here, we can also do resonance. So let's take a look at this furthest one on the left. If we push one electron down here, an electron comes from our double bond to make a different double bond, and then we can shift a radical, half arrow, to this last position. So this will give us something that looks like, nope. This now. And because this is a unique structure, it's going to make another product that we don't have previously. I'm going to kind of box out these, keep them away from our actual products. So it's going to give us a different product. Looking at our next one, we can do a resonance structure. All these are going to have one resonance structure. This lets us shift our double bond. Don't believe anything looks like this so far, so this is going to give us another structure. BR goes where the radical was. And then, ooh, I think this one might actually give us something that we already have. So we shift this one down, this one over here. I think this gives us the same structure. Yep, so these two are the same structure. We don't need a second product for this one. Okay, I'm going to give you guys 2 of these to work through. I'll give you guys some time to work on them, and then we'll take our quiz and be done for the day. So let's see. I'm going to make one of them a little easier, one of them a little harder. This first one should have a lot of duplicates. Yep, you can use notes in the quiz. They're open note. I don't like how I drew that. All right, let's do these 2. So I'll give you guys till the 51, maybe 52 to work through these. And I'll check back in with you guys. All right, so I'm gonna erase this for the second one. We'll go back to it in a second. In terms of allelic positions, we have 4 of them. Luckily, because there's so much symmetry in this molecule, 2 of them are the same, or I guess you can group 2 of them together. So these 2 are the same, as well as these 2 being the same. So because of that, we can ignore one pair. So I'm going to ignore this top pair and only focus on the bottom ones. If you did the bottom ones, you'll still get the same answers. Or the top ones, you'll still get the same answers. So let's take a look at these 2 bottom positions. We can draw in radicals for them. A little better. So each of these will lead to a product. They both will have resonance. So we can shift this electron in, make a different double bond, kick that radical up. Make a new radical here. This will lead to a product that is unique. Same thing with this other one here. We can get a different resonance structure. Which will lead us to a different product. Are there any questions on this one? Nope, not a radical. That should be a product. BR there. Okay, I'm going to go through this next one a little quickly. We're a little low on time. So we've got, let's see. This here, we're going to get 3 different radicals for our 3 different allelic positions. So we should get one here, one here, and one here. All of these can lead to products. And we're out of room. And they all can have resonance structures. So we shifted the resonance structure for our first one. We would get now a double bond here, a BR, doing the same thing for the next one. Shift our double bond to this position, giving us the radical here. And then for the last one, putting our bromine in this position. So these are the 6 possible products from these. I probably won't give you one that's this complicated on an exam, but just so you guys know how to work through these, you basically figure out all the allelic positions, and then they all should have one resonance structure at those spots. Okay, I'm gonna have you guys turn on your camera. We are gonna do a quick quiz, and then we will be done for the day. All right, so just 2 questions. They are multiple step. You guys are welcome to just draw the major product. If you want to draw in steps, that's also fine.